Okay, I'm going to keep this video fairly short because I'm still kind of recovering from a concussion I got Wednesday morning from a fall I had. So hopefully this video is not too loopy. Um, but let's go just do a quick review of what a covalent bond is, and then I'm going to show some Lewis structures. We're going to focus on just on single bonds for now, and then in the next lesson go to double, triple bonds. So let's look at basic covalent bonding with Lewis structures. If I look at what a covalent bond is, here's for example hydrogen. Simplest atom there is. And so hydrogen is this, and then here's another hydrogen. Both of them are short what they need for a complete full valence shell, which for hydrogen, since it's in the first unit, that's the only shell that's full with 2 electrons. It needs 2, it only has 1. So yes, it could add, but that's rare that hydrogen will actually add 1 to become a negative ion. More likely, it will share, sometimes with another hydrogen. The 2 hydrogens come together and say, well, we're both short 1, what if we share? And they do. If I have a sample of pure hydrogen, it's in the gas state, and it is in this form. Hydrogen, you don't find hydrogen if you have pure hydrogen. It's not hydrogen atoms just hanging around by themselves, bouncing around. It is paired up hydrogens. Why do they pair up? Because by pairing up and sharing those electrons, they have their full valence shell, and that is the stable state. Now, we don't generally use Bohr models when we're trying to show covalent bonding because Lewis structures are so much simpler. So let's look at the Lewis structure for hydrogen. Here's its 1 electron, which of course is a valence electron because it only has 1 shell. Finds another hydrogen. They form the bond, and that is called a covalent bond, which is a shared pair, of electrons. So they form a covalent bond. Now that they're sharing those, each one counts those electrons as fulfilling its need for a full shell. So this hydrogen has 2 electrons, full shell. This hydrogen has 2 electrons, full shell. And that's a covalent bond. Let me use another example. We talked about it a little bit in our lecture, first opening lecture on this. Of course, hydrogen doesn't always bond, and normally doesn't bond with just hydrogen, with other things. What about hydrogen and oxygen? The most common molecule that contains hydrogen and oxygen is water. Hydrogen has 1 valence electron, needs another one to have 2. Oxygen has 6. Since it's in the second period, a full shell in the second period is 8, not 2. So this hydrogen comes in, shares. And then oxygen now has 7, including this shared one, but it needs 8, so it finds another hydrogen. Now, generally, we'll show these covalent bonds, these shared pair, as a line. Not always. It's okay to show it like this. And I have that. The molecule is H2O, water. There's different ways that H and O can bond, but let's look at that one later. And of course, so what I have is 2 covalent bonds. In a water molecule, there are 2 covalent bonds with shared electrons between hydrogen and oxygen. And there are 2 pairs that oxygen, this pair and this one down here, that oxygen is not sharing with any other atom. So that we call them unshared pairs. So here's a shared pair, which is a covalent bond, and here are unshared pairs. Most molecules do have a combination of shared pairs and unshared pairs. Then, of course, if I look at what about hydrogen and sulfur. Same kind of arrangement. Now it's a different molecule. It's not water, H2S. Hydrogen sulfide is definitely not water. But the way hydrogen and sulfur interacts is the same as the way hydrogen and oxygen. Why? Sulfur, like oxygen, also has 6 valence electrons. So it finds 2 hydrogens. And you have this one with the molecule H2S. So they interact in the same way. Of course, these two molecules have very different properties. You don't want to drink this stuff, and don't drink hydrogen sulfide. But they have very similar in the way they interact. So that's what's similar. How they interact with each other is very similar to form that molecule. Now, let's look at some of the most common compounds. They're called organic compounds. What about hydrogen and carbon? There's a whole topic of organic chemistry that we'll just barely touch on in this class, but carbon is, you could say maybe water is, but really carbon is the atom that builds life, right? So what is so special about carbon? Here's hydrogen. What's so special about carbon is it's a small atom, and because of those 4 valence electrons, it has an ability to combine and form complex molecules like nobody else has, right? So if it's just going to be, so there are so many different ways that hydrogen and carbon can interact, that in fact that this type of compound is called a hydrocarbon. But of course the simplest way, this carbon only has 4, it needs 8. What can it do? Hydrogen comes in. And so now the carbon, with including the sharing, has 5. It's gone from 4 to 5. So it says, well, let's keep this going. Finds another hydrogen. Finds another hydrogen. Finds another hydrogen. And that's CH4. So in this case, there's no unshared pairs in this. So all the molecules are being, all the valence electrons are being shared. Notice I said all the valence electrons are being shared because carbon has a couple of inner shell electrons. So inner shell electrons are never involved in covalent bonding, only valence electrons. That would be the molecule of CH4. That is methane gas. It's found in a lot of, well, it's the gas that's pumped through houses for gas burning and such. There are other ways that carbon and hydrogen can combine. How else could they combine? Well, one of the things that carbon has in its ability is, because of this arrangement, carbon can actually form these big chains, and so those are the organic molecules, the proteins that you learned about in biology. These long chain, just a long chain of carbon atoms. So let's form a chain. So here, this carbon bonds with this carbon, and they're starting a chain, but we're going to make this chain 2 carbons long. And then let's give them their full octet. So now this carbon only needs 3 to finish it off, because it's got 1 pair it's sharing with this carbon. This one also needs 3 to finish it off. So that's one of the many molecules that are formed by combinations of carbon and hydrogen. Of course, these things can keep growing. There's also C3H8, C4H10, C5, etc. They can get longer. Gasoline, the octane rating in car gasoline has 8 carbons connected and 18 hydrogens along the outside. So these are the hydrocarbons. A lot of our fuels are carbon and hydrogen bonds. We'll learn why later. So what is this one? It's generally drawn this way. Again, in these CH combinations, there's no unshared pairs. C2H6. Now there's other ways. We'll look at one more molecule. Let's throw an oxygen in there. Because also these organic molecules, or the molecules that make up your body, a lot of them are mixtures of carbon, oxygen, hydrogen, nitrogen, etc. So let's look at one. And we generally write this CH3OH. This is methanol. CH3OH. Now, why write it there? Why not write it CH4O? Like, why do we separate those H's out? Because this is a hint on how this molecule is put together. What this says is 3 hydrogens are connected to this carbon. The carbon and oxygen we're going to connect because hydrogens can only make one bond, so they're always around the outside. They can only make one bond because for them, one bond, 2 electrons, is a full shell and they're done. So hydrogen would never be in the middle. We can throw it in the middle here because we can say these 3 hydrogens are attached to this carbon. This hydrogen is attached to the oxygen. So let's build this. Whereas writing it like that doesn't give us that information. This gives us more information on how this molecule is arranged. It says, let's take that carbon, and the hydrogens are going to connect it here, so let's connect it to the oxygen, which was like this. So let's snap that oxygen in here. Right, so we've snapped the carbon and hydrogens together, and then we say, all right, give this carbon 3 hydrogens. And then it says the last hydrogen, based on this, the last hydrogen is connected to the oxygen. Let's simplify this by showing the covalent bonds, or the shared pairs, with a line. C, H, O, H. And don't leave these dots, these unshared pairs, off because they are important. Even though they're not bonding anything, what are they doing? They are actually affecting the shape of this molecule, which affects how it interacts. So the unshared pairs do actually have a role to play in determining the shape of the molecule. So here it is, CH3OH, and it's shown like that. So I have a document that's attached to this assignment that we will just practice more of these Lewis structures, and then we'll move on from here into some compounds that use double bonds and triple bonds in the way they share.